Good morning, everyone. First of all, thank you, the organizer, for a good event and opportunity to present my work. I will be talking about a Fabit precursor, and I will start with introduction you Fabit. So Fabit is basically a focused electron beam induced deposition, and the experimental processes basic schematic is depicted here. We have some precursor blown onto the substrate, and the tightly focused electron beam is used to cleave metal ligand bonds. Ideally, all of the bonds are cleaved and pure metal left behind on the substrate. So these techniques enables to direct write 3D nanoprinting of a complex nanostructure, as you can see here. Now let's talk about 3-methyl cyclopentadienyl platinum, and in the rest of the presentation I will be just talking about platinum precursor because it's easier to pronounce. So this precursor is commonly used for platinum depositions due to its favorable vapor pressure and exceptional thermal stability. However, this fact is counterbalanced by this low purity of platinum deposition in Fabit experiment, which is interesting because in chemical vapor depositions, the performance of this compound can be easily achieved by 99% of purity. These differences have stimulated interest in the mechanisms of electron-induced fragmentation of the platinum precursor. And the primary question is how many and which ligands are removed from the precursor in collisions with electrons. While the electron energy of primary beam is in the kilo-electron-volt range, the main focus has been on the electron with energy of 10 electron volts, since the radiation-induced chemistry during the deposition process is primarily influenced by low-energy secondary electrons. Another motivation for our research stems from the puzzling results with previous surface studies. In these studies, the multilayer condensed film of platinum precursor were deposited on tantalum substrate, and electron-stimulating desorption techniques employed to study electron-driven chemistry. And they revealed a very surprising phenomenon. Contrary to expectation, there is no methyl radical was primarily released from the substrate, but rather methane or small amount of ethane molecules. There are three basic mechanisms of how electrons can cleave metal ligand bonds: is dissociation ionization, dissociative electron attachment, and neutral dissociation. So here we have our experimental setup on the right side of the slide, and basic schematic of the reaction. So basically we have a precursor, and we irradiate the precursor with electrons of controlled energy, and then positive mass product was analyzed using a reflectron time-of-flight spectrometer. Here's presented experimental result. On panel A we have a cumulative mass spectrum on electron energy from 5 to 20 electron volts, and the spectrum is rich due to the fact that platinum has 5 major isotopes, and varying number of hydrogen atoms can be cleaved from each fragment and contribute to the peak. But nevertheless, there is easily identified 4 major group of peaks. From 315 to 325 we have parent cation molecules, and 3 group of peaks from 270 to 310 corresponds to the loss of 1, 2, or 3 methyl radicals. On panel B, we have a variation of mass spectrum on energy, where its intensity is color-coded. A general trend for such a 2D ionization map that the more molecule you have fragmented, the more energy you need to add to cleave the covalent bonds. But there is a different trend here. The appearance energy for the loss of 2 methyl groups is lower than the loss of 1 methyl groups, as you can see. This means that their fragmentation channel, which leads to the loss of 2 methyl groups, is energetically more accessible. To address this question, we performed irradiation-driven molecular dynamic simulations accompanied by quantum chemical calculations. ITMD methodology allows to analyze fast energy transfer into fragmented covalent bond caused by quantum processes. This simulation were performed using MBN Explorer software package and reactive force field. It's important to note that this force field allows to change some properties on the fly on the simulation. For example, bond dissociation energy, partial charges, cleavage of the bond, or formation a new one. Yeah, and this simulation was accompanied by DFT calculation, where we have obtained an optimized structure, bond dissociative energy, and force constants, and partial charges, which is required inputs parameters for the reactive force fields. Also, we have calculated the appearance energy for the main group of peaks and created a potential energy surface, which I will show you here. So here is a contour plot where you have on x-axis the distance between C2 and C4 atoms, and on y-axis distance between platinum atom and the center of masses C2 and C4. The color is a reference to the energy difference between particular geometric with this characteristic and optimized structure. This contour plot has two distinct minimum. One is optimized geometry, and another one is geometry where ethane is formated. This pathway proceeds through the transition state, which has energy 0.9 electron volts, which is lower than the energy required to cleave a covalent bond for the platinum C covalent bond, which is 1.5 eV. On the left side is depicted on the only negative vibrational frequency for the transition state, which is a key characteristic for transition state and indicates there is a saddle point on this reaction pathway and reflects instability of this structure. Also, it needs to be mentioned that the interatomic distance between platinum C atoms is only 0.2 angstrom longer than equilibrium distance. And we assume that when the metal groups have enough energy to overcome the barrier of transition state and then they approach each other, the simultaneous cleavage of these two covalent bonds leads to their ethane formation. Here on the right side we have a short video of from the MBN Explorer simulation which leads to the ethane formation with transferred energy of close to 8 electron volts. On the left side we have overview result relative abundance for the four major species, and the star marks indicate the ethane formation of this reaction. On x-axis we have transferred energy to the neutral molecule, and this line indicates the adiabatic ionization energy. On the graph, it is clear that in low energy, the main reaction pathway it's loss of two metal groups, which accompanied by ethane formation, which is perfectly copied the shape of this red curve. When the molecule has enough energy to overcome the barrier of covalent bonds, there appears of fragmentation of one metal groups, and above 12 eV, the dominant channel is fragmentation of 3 metal groups. And the conclusion is that the separation of 2 metal groups accompanied by ethane formation are energetically more accessible, and this explains the present experimental results. and partially explain the result of previous surface studies, and this can contribute to the low purity of platinum deposits in FABIT. I would like to acknowledge my supervisor Juraj Fedor and my colleague Jaroslav Kočišek from our institute for their help in experimental part, as well as Alexey Verkhovtsev and Andrei Solovyov for their help in IDMD simulation. Thank you for attention.
Thank you, Hlib. Do we have any questions about this? Yes, there is one question from Professor Yanes in the back.
Nice talk. I have a question and a comment. I realize that in your theoretical simulations you have used a DFT formalism with an empirical dispersion correction, which is a wise choice.
Yeah.
But my question is, have you included also relativistic effects? And if not, do you think that they can have some relevance in your analysis or not?
No, we don't try to do it because we have this irradiation-driven molecular dynamic, and this methodology is widely used for FABIT precursor with another molecule such as iron pentacarbonyl. So they have a methodology to account these quantum changes, the rupture of the bonds and the formation of new one. But probably the some relativistic effects can influence on this. But this project is taking us almost 2 years, so probably it will be the next step. Yeah.
My comment is concerning the imaginary frequencies when you have a transition state, in the sense that your conclusion is probably totally correct in my experience, because you know the accuracy of the method precisely in the transition states is not the same, and the one you have when you are dealing with an equilibrium local minima in the potential energy surface. So very likely these values that are normally not only imaginary but small have a significant error, and sometimes overestimate the barrier of the process you are looking at. So I think your conclusion is normally quite correct.
Yeah,
congratulations for the talk.
Thank you. I spent 1.5 years to build this control plot, and here is like 1,000 points, so it was quite hard to identify the transition state, but yeah, thank you.
Yes, we have a question here.
Yeah, very nice work. Yeah, sorry to hear that you were 1.5 years doing surfaces. That I've also experienced it myself. It's very tedious. So following up on the relativistic effects, did you calculate any other surface of any other multiplicity and calculated spin-orbit coupling just to see if it could be mediated by spin-orbit coupling effects?
We have tried to calculate the multiplicity of their parent cation molecule, but the energy was higher than the single. Again, so we have a multiplicity in the duplet or singlet state based on the amount of electrons, and for the parent cation molecules we try also at quadruplet, but the energy was higher, so we don't go ahead and don't provide more calculation for another fragment.
Okay, thank you.
Thank you.
We have one question here in the front from Sylvain.
Thank you. Thank you for the talk. How are you sure, like for instance, when you showed with the simulation quite well that the two methyls are the ones that are attached to the platinum.
Yeah.
But for instance, when you lose the third one, you know if it's from the platinum or if it's from the cyclopentane, you know?
I'm mostly sure that it's from the platinum, because the bond dissociation energy for this is lower than from here. So it's easier for platinum to cleave these bonds. Yeah.
And there is no plan for, I don't know, like a deuterated methyl to be sure?
In these studies we it was interesting from puzzling results from surface studies that they have methane molecule and ethane. We have no here methane because we have single collision experiments, so we have no much hydrogen atoms, but we successfully find the transition state which is lower than so that was the main study.
Thank you.
Thank you.
I will ask a very quick question, although I have many. Very interesting work. So what is the time scale of your process of fragmentation, and how does it correlate with the energy?
I can talk about like 20 minutes, but I will try. So here we have 1,000 different simulation for different different starting geometry for these molecules, and the energy transfer in this methodology applies like scaling the velocity of the atom in the molecules.
Yes.
So the time scale of the reaction in ambient explorer is easily achieved typically 50 nanoseconds, but in this experiment we performed like half nanoseconds or 0.8 nanoseconds because we have quite a big simulation box, 800 for 800, but the fragmentation is it takes in very fast, and your fragments start into collision with the main molecules, which cost you. And after this, it is not more single collision experiment. So because of this, we reduce the time of the simulation, but it's possible to go to the probably microseconds if needed.
Yeah, but then it means that it's probably below 1 nanosecond, the whole fragmentation process in your simulations.
Yes.
Very interesting. Thank you. Let's thank Hlib once again.